And on the y-axis is also 0, 1, 2, 3, 4, 5. Okay, and at each node here, you just put the numbers on the y-axis in the numerator, and put the numbers in y-axis in the denominator. So you will get 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1 on your first row. And for the second row, you will get 1 over 2, 2 over 2, 3 over 2, 4 over 2, etc., etc. Okay. So in this way, we can collect the positive part of rational number, because the way we construct the rational number is not yet, but like we will have some repetitions, which we are going to remove later. But conceptually, you already have the positive part of the rational number. Okay, so put them together in a list. So you will get the list look like this one. This is the first step. The second step. The third step is to remove the repetition. For example, like 2 over 2 is equals 1 over 1. So you remove that one and keep the unique part here. So you will get the positive part of the rational number, which is the big Y here. Okay. So far so good. Good. Okay. Then we continue. Okay, so continue. Our goal is to find bijections from natural numbers to rational numbers, right? So what is our domain? Domain is the natural number, which contains 1, 2, 3, 4, and continues. And the target is rational number, which is the set y and the negative part, like the negative corresponding part of it, which is, I put negative y here, and also 0. Okay, so this is the target. Okay, and then we are going to construct the functions now. We assigned the first one, like f of 1 equals to 0, And this is the list of positive part of the rational numbers, 1, 2, and 1 over 2, and minus 1 look like this one, minus 1, minus 2, minus 1 over 2, and we start to assign. Okay, so for the 2, f of 2, we assign 1, f of 4, assign 2, and etc. etc. And we can do it for the negative part, which is f of 3 equals to minus 1, f of 5 equals to minus 2. And then we find such bijections. So the cardinality of natural numbers is equals to the cardinality of rational numbers here. Okay, so so rational number is countable. Okay, because we find the bijections here. Yeah.
Do I have to write bijection under arrow to indicate that it's a bijection? Because just an arrow can mean other things.
Arrows to.
From N to Q.
Oh, that is when I wrote down a functions. It means the functions, the domain of the function is the before the arrow, and then after the function you will transmit the elements from the domain to the target area there. So that it means that is used in the function to represent, to show you the direction. It's not means implied or some other stuff. Yeah, but when you write down the proof, like I should say that when you put the arrows in the proof, that means most of the times it means implied, like statement A implies statement B, and when you put the double arrows here, so that means equivalent. Okay, so that is kind of different and kind of, in my point of view, it's kind of abuse of simple here. Okay, does that answer your questions?
But do we have to write bijection like there?
No. You mean, do we have to write it down this to represent bijection functions? Is that your question?
No, just because the goal should be that the arrow is bijective.
Yeah. But how should I put it? Because the functions, when you talk about function, it has the directions from one set to another set. So this arrow is to represent the directions. Okay, so I don't think it makes sense when you define a function and you put, says that, okay, it is, even it is a bijective function, you don't have to put an arrow look like this one. Yeah, it doesn't make any sense to me at least. Yeah. Yeah.
What's the reason you construct the table with this?
Oh. What is the reason? Oh. What is the reason I use this table? Because that's the way I learned how to improve it. So I think the reason is that you have to have the list of rational number first, because we want to assign the function from natural numbers to rational numbers, right? And if you construct, or like if you have your list randomly, for example, like how many, let me ask this question, how many rational numbers between 0 and 1? Infinite, right? Then you randomly put up orders here, or you randomly construct it, then you will easily get lost, when you try to write down, when you try to assign the functions. Okay, so this is how to say that? So in this way, it is easy to put down, to write down the list in a way that you are not going to repeat and you are not going to miss any numbers of it, any numbers in the rational number. Okay, so I guess that is the reason here. And also, if you look at the definition of rational numbers, it defines as Q over, like P over Q, right? So it's actually is two like numbers, and that is XY plane, right? So I think this way will be more intuitive. Yeah. And of course, this is not the only way to